which can be downloaded at scp.org, and has a lot more information about the causes, the scientific causes of why these things happen, and some more examples of what they look like on full band capture tools. Okay, into suckouts and resonant peaks. You want to define suckouts for us, Larry?
You bet. This is one of my favorite, and it's really commonly misunderstood about what exactly a suckout is. We know what the mechanisms are that cause them, but what is it really, and how do you explain it? And so I learned an important lesson on, this was over a decade ago, when we created a microreflection. It was standing wave. We took this long cable and we started cutting it, and then you could see the waveform of the standing wave, the lambda, the length of it, shrinking. And so you cut it, and you cut it, and you cut it, actually, sorry, growing. So the shorter the reflection, the wider the standing wave. And sooner or later, when you cut that cable short enough and create a microreflection, it results in a standing wave where the second incident of that wave is so far out of the spectrum analyzer you can't actually see it. So what you're actually looking at in this like upper left-hand corner is a half of a period of a standing wave. That's right. And so in order for, if we did the math on this, in order for it to result in a suckout in 1 gigahertz of visual spectrum, the reflection mechanism has to be 6 inches or less. Now it's a little more precise than that. So generally, when you're seeing a suckout, if you could, in your mind, perceive, say, 3 or 5 gigahertz wide of fully occupied spectrum, you would see more periodics. And then the shorter you cut that, the less and less you'll see the periodics of it. So only that's a half of a standing wave, and short is what you're looking at. And so that whenever you see a suckout, you're talking about a very small area for a reflection in an impedance mismatch. And this is all of the stuff we're doing all day with loose connectors, housing, screws, corrosion, and typically it's in a mechanism like a tap circuit or a circuit board, because the traces on the circuit board, if you get a corrosion on a pin or a screw on a circuit board, it's actually creating a microreflection on the circuit board rather than the cable. And so those are where you'll see these 6-inch or less reflective cavities that result in suckouts.
This is super fascinating. So like you, once I learned what actually causes this, when I look at a suckout, I think really big standing wave. We just can't see the other nulls, right? And when we look at standing waves, we see a bunch of mini suckouts, right? So there's an interesting relationship there. But thinking about it through a plant maintenance guy's perspective, the devices that are 6 inches wide, right, which is sort of the criteria for this really long standing wave, the half period of the really long standing wave, directional couplers, splitters, tabs, right? Those are the components.
Everything on our plant, everything, yep.
Now, the other part of that is that those small devices, right, the 5 to 6 inch wide devices, are also really good mini slot antennas if there's corrosion and the shielding is defective, right? So at that frequency, they tend to resonate leakage really well in high frequencies like 600-700 megahertz. So oftentimes when you see a suckout, you may also have a leak at 600-700 megahertz because of the relationship of the geometry, the size of the component, and the fact that it's defective, meaning water corrosion or something impaired. So it's not uncommon to see high frequency leaks and suckouts associated with the same things. So when you're chasing a suckout, turn your sniffer on.
Great tip, love it. So another thing about suckouts is that we describe them in different ways. They have generally a center frequency, and that's where is the null? Where's the maxima of the null, and how wide is it, and what's the magnitude? How deep down does it go from the signal? And so in this case, we would describe this, and this is how we would potentially, and we do actually, um, determine the severity of these suckouts is the magnitude. How much of the frequency spectrum are they actually interacting with? What's the center frequency? What's there? There's a lot of different properties. There's actually 4 significant properties of a suckout that help us determine, how important is it or isn't it. So just a little interesting factoid about suckouts. This is a good example. Like I said, I remember this was Jason Chapman at the time. The important thing to notice about this suckout, this was just a loose screw, and notice that the center frequency of the suckout is right on that pilot, that AGC pilot. And what happens then is these things can oftentimes be change and move, yes, depending on the physical characteristics of that impedance mismatch. And one of the things that affects those a couple of things, environmental mostly, temperature. So if the sun hits that thing and it warms up, or if it gets cold, the temperature can change the physical characteristics of that impedance mismatch and cause that thing to float around and go up and down. And guess what happens when that suckout comes and goes on that AGC pilot? You have this cascading effect throughout your amplifier chain. You know what happens with AGCs? It's a regular roller coaster ride. That one suckout is actually, even though it looks small, it's only 10 dB, but it's on the AGC affecting the entire cascade. So this is Mike's famous wobble event all day long. When you see that AGC being hit by one little bitty suckout coming and going, the cascading effect on your amplifiers is massive level changes, and it's not good. So
that's a great point, Larry. When we talked about like what channels are represented in this full band capture, you can see this CW carrier at 429 megahertz. That's our ALC pilot. So knowing where your ALCs are and whether they're analog or digital can influence the priority that you put on that suckout. Not that the suckout itself isn't important, right? But if those were just linear video channels in there, it may cause some, tiling problems on a customer set-top box if they're tuned to that particular QAM. But if it's the analog ALC pilot and that suckout is moving, to your point, or varying over time, that can cause huge instabilities in your plant and create artifacts or impact every line of service. So to take that extension a little further, if the ALCs are trying to correct for a pilot that is part of a suckout, it's going to amplify all of the output of the entire spectrum, not just that narrow portion. So it'll increase the output power of the channels that are not affected, which then increases the input to the next amplifier and can cause that amplifier to go into compression or distortions, which would affect every channel in the lineup, regardless of whether it's part of the suckout or not. So suckouts are important in and of themselves, but if they influence the ALC pilot, they become exponentially more important.
yes, and sadly we see too many amplifiers out there that are set up a little too high, running hot on the NPR curve, and if you all of a sudden have a additional gain on the front end of those things, you can only add 1 or 2 dB of power and start to see 5 or 6 dB of noise because of the compression function of that amplifier circuit. So good point.
Okay, so interestingly enough, I'm in Monroe, Louisiana today, visiting one of our Comcast systems, and we had a very animated discussion about this mold spike suckout. And what this is a artifact from certain types of hardline cables that when they were made not with dielectric foam separating the center conductor and the outer conductor, right? If we think about cable construction and the way it's made is you have an outer conductor and a center conductor, and the material in between them is very important because part of the impedance of the cable is determined by the ratio of distance between the outside of the center conductor and the inside of the outer conductor. So this particular type of cable, the way that distance relationship was maintained was with a thin plastic disc that held the center conductor in the center of the cable. Well, where that disc connects with the center conductor, it creates a very small impedance mismatch. Now, the discs, when they're evenly spaced throughout the length of the cable, is a long series of impedance mismatches. And depending on the distance between the discs, it actually determines the frequency at which that summed impedance mismatch starts to turn into this suck out. And the more cable that you have in cascade, the longer the cable length, the more impedance mismatches piled together, the deeper the suck out gets. So that's called a mold spike suck out. MC squared cable that you may have used before over generations from the 1960s through the 1990s identified this mold spike based on the distance between the discs. And as the cable generations got newer and newer, they moved the discs farther apart, which pushed the mold spike out past the usable band of interest. But previous generations, that mold spike fell right into the usable band below 750 megahertz. So you may say, well, I don't have MC squared cable in my system, so why do I care? Well, the truth is you can create this in a drop system. Let's say you're installing an outlet on a customer's house from the ground block, and you have to wrap the cable all the way around the house, 200 feet to the other side of the house to reach the outlet that you're trying to run. So you take your cable grips and you install them every 18 inches precisely all the way around that house, and then you zip tie the cable to those cable attachments. And every time you put a zip tie around that drop cable, you squeeze the cable just slightly. And that creates a small impedance mismatch because you change the ratio of the distance between the outer conductor, in which this case is braid, to the center conductor. So you can actually create this mold spike with soft drop cable by installing zip ties at very precisely spaced distances over time. So even if it's not MC squared cable, if you see this response, it could actually be zip ties on a piece of drop cable that are creating this suck out. Super cool cable nerd stuff.
Just for the record, I've never seen perfectly spaced zip ties in any shape or form on any drop cable ever, but it's conceivable that that could happen.
It is conceivable, and actually I saw it on one of the Facebook cable dudes pages where they had a technician that used to take a tape measure and measure very precisely where he put the cable ties, run his outlets, and it actually caused a problem. It's been documented.
Now we know.
On to
All right,
resonant
so
peaks.
let's move on to resonant peaks, and we're doing a time check here. Okay. Resonant peaks are interesting, and we have seen these over the years. And if you've been around driving a bucket, it's not a new phenomenon to you. But resonant peaks are actually, the thing that's unique about them is that there's a gain component to a resonant peak. That means there's additive signal. And to have a gain component, by definition, it has to be on an active piece of equipment. And in this case, we know that it is caused by amplifier circuits. And so that gain component was a very interesting experience for us to learn about how we can use this to our advantage. Basically, well, there are several things that can cause this, but what we typically see is corrosion on the modules where and these tend to be affected by temperature and environmental influences, and they'll come and go quite a bit. but the corrosion on the amplifier module will cause an oscillation within the circuits within the gain stages and result in these types of peaks. And yeah, remind yourself when you see a peak, null is one thing, that's actually attenuation. Peak is additive. There's additional gain component. So think peak amplifier, and you'll be in service of getting you to that problem. Mike, talk a little bit about the field perspective about resonant peaks and what we do today and what we should do and what we don't do. And I got my own perspective, but I'd love to hear yours. You're the dude.
So some of the things that we do that we probably shouldn't is we can look at our full band captures and say, hey, all of the modems or full band capable devices after this amplifier all share a resonant peak. So how do I fix it? Well, I can go open the pedestal and kick the housing and it'll probably go away. Or I can take my layup stick off the truck and give the amplifier a good whack of its aerial, and the resonant peak will probably go away for a while. But a lot of things happen, especially in aerial cable, but also in underground cable, where you mentioned the environmentals of temperature and weather and humidity, moisture, those types of things. Some of our amplifiers have been in service for 20, 30 years, right? Especially in the aerial locations where they're subject to a lot of heat from the sun, from wind, from vibration, from a lot of things. And those amplifier housings, many of you know, they have very precise tightening sequences to close the amplifier housing properly. And you also know that inside of the amplifier, the module retainer screws do have torque specifications so that the module is firmly seated in the housing and is properly tightened, and then the housing is properly tightened. But over years, through normal wear and tear and environmentals, some of the gaskets on the housing may deteriorate, water may migrate and get corrosion inside of the housing, particularly the RFI or the shielding gaskets that's in the housing, or the module retainer screws may loosen over time because of vibration and wind whip and things like that. And so the housings themselves can actually warp or twist. And when that happens, if the module doesn't warp or twist exactly the same as the housing, maybe because the module retainer screws are loose, then we can create these peaks or these cavitations or oscillations inside the amplifier. So a lot of cases, just opening the module or the housing and tightening the module retainer screws in the absence of corrosion will make this go away, because the module has torqued or warped inside of the housing. So then when we close the housing, it's important to check to make sure that it's free of debris and corrosion, particularly on the RFI gasket that seals the clamshell when it's properly tight. And following the proper torque sequence when closing the housing may ensure that it doesn't come back. But in a lot of instances, you can go and just whack the housing and it goes away for a while. But if you don't properly check for corrosion, for tightness, for warping, there's a very good chance that it's going to come back.
Yeah,
I did want to pause there.
comments on that. Yeah, let me jump in really quick. There's two things. Resonant peaks, just like suckouts, you have a different amount of severity, but if that thing, the peak is peaking on the ALC pilot, then you have the same phenomena where you have the cascading effect. Like what could be a kind of a minor thing, 5 or 6 dB of peaking at a given frequency, okay. But then if that thing is having this cascade effect on your amplifier performance and distortion and compression, these other things, then you might have a real problem. So pay attention to this. And I have almost always see, like, we just go boot the pedestal and it goes away. Like that's very temporary. You guys already know that, because it comes back and it's a function of that mechanical interface. So take an extra minute, maybe pop the module completely out. I know that can impact the customer. Put the module back in, hit all of the screws. Again, like, who do you see out there with a torque wrench? Not very often, but consider getting a torque wrench, but absolutely the torque sequence. Like I'm also do mechanics as a hobby, and everything I always fix, I do a torque sequence on. And if you don't know it, just opposite corner, right? Like it's not that complicated. Um, and anything is better than just going in a circle, tightening it as tight as you can go, and that results in incorrect torque being applied to the mechanical interface. So anyway, had to weigh in on that, Mike.
Hey, we did have a question from Derek, and we're going to go back to, I think this was the slide that he had the question on, where you had that really great suck out on that amplifier. And the question was, which seizure screw was it
I see that.
that
Yeah, I
caused
got
it?
this back from, I'm pretty sure it was Jason Chapman way back like 10 years ago. He's in the field. I don't know which one it was. It was just an email response, and it was a, it was a loose screw. Don't know which one. Sorry to say. Don't know.
Sorry, Derek. But the important part is that all of the seizure screws and proper tightness are important. So, okay. So back to resonant peaks. So these were some examples of actual resonant peaks and the amplifiers that cause them. So we included the pictures not to protect the guilty, um, but it can happen on any amplifier, and we'll see other examples. Now, the interesting thing is that the size and shape of the amplifier does actually have impact on the response of the resonant peak. So we see different amplifier types out there. This one happens to be, the Cisco Gain Maker platform, which has a very, rectangular shape, and the placement of the module retainer screws inside of the housing in the presence of corrosion, and the different types of connectors that are used to interface between the RF module and the housing. In this case, it's the lugs, right? Can actually start to develop patterns in their resonant peaks. So amplifier modules like this Gain Maker may have a very specific resonant peak signature. So in this case, taking the module out, checking for corrosion, ensuring that the seizure lugs in the housing are tight, making sure that there's no corrosion on the connectors on the back of the module, and then properly tightening the module retainer screws into the housing and properly closing the housing will result in the response that you see on the bottom, which is everything's nice and flat. We do have a little bit of a peak still in our OFDMA, but that's not the same as the resonant peak. You can see that was still here when we had our significant resonant peak impairment. So different amplifier modules may result in different resonant peak types. Now, if you do go to the SET OP280 document, you'll see we have several different amplifier types that have different resonant peak responses. But it's just important to reiterate that these are typically caused at amplifier housings. They're often a result of corrosion or improper tightening of the module into the housing, or they could be warped housings and or modules that don't allow for proper tightening and mating inside the housing, or those types of things. So more on resonant peaks, cause, and responses in the OP280 document, but this is a really good illustration of what a resonant peak can look like,
Yeah.
and what the resolution is.
Mike, could you go back one more slide too? Like you touched on it. The three different peaks you see here, they're at different places in the frequency spectrum and in slightly different shapes. These are three different amplifier types. So you'll see, pick your amplifier of choice. They will all have a very distinctive shape and size and location. So these are, I'm not here to pick on names and types, but I can tell you each one of these is a specific manufacturer and generation of amplifier and gain stage design. That's what determines where the peak is, and the magnitude is how bad the corrosion or whatever is, but the shape and the location is all about which manufacturer is it. And so the one in the lower left-hand corner, you may be like, that doesn't look like the rest of them. Well, it doesn't, but it is a resonant peak. It's just caused by different gain stage design. And the last one to leave, and then we'll move on to the next topic. We got to get going for time here, is that you might just go tighten a connector on a housing on an amplifier and see the peak go away. That's basically the same thing as hitting it with a hammer or kicking it with your boot. What you're doing is you're imparting a vibration onto that corrosion mechanism and basically clearing it and it's going to come back. So don't be fooled into just tightening a connector on the outside and thinking you got it. Like it's going to be back. So without opening the lid, checking the screws, torque, get the torque order, tightening order, and it'll serve you well and not have to be back there again. So carry on, Mike.
So the cool part is if you start to connect the dots between the shape and the frequency response, or the frequency of the resonant peak to a particular amplifier model, over time you'll start to look at a response and go, oh, I know which amplifier that is. Not necessarily which precise amplifier until you do the correlation of how many devices have that same impairment, but you will know which make and model